Hello everyone, my name is Subodh and I'm here to present our paper titled Target Tree Extrinsic Calibration of a 3D LiDAR and an IMU. Here is a brief overview of the presentation. First, we are going to introduce the problem of calibration between a LiDAR and an IMU. Then we are going to present the calibration algorithm that we are going to propose. After that, I'm going to describe the system of sensors we have used to validate our algorithm. Then we'll move on to the experiments we have conducted with those sensors. And finally, we will conclude the presentation with a summary. So LiDARs have been in use in robotics for quite a while. And most of the LiDARs that are being used these days are spinning LiDARs, which have a spinning mechanism inside them, which generates the 3D point cloud of the environment. Now, the problem with the spinning environment is that, with the spinning mechanism is that it gets distorted. The resulting scan gets distorted due to robot motion, and especially when the robot motion is really fast. And an example of that can be seen in figure 1, where we can see that the cardboard, which is basically square in shape, is distorted. It's like broken or sheared in the middle, and the square cardboard does not look square anymore. This effect can be removed by using other sensors, for example, an IMU. And you can see that in figure 2, where the cardboard actually looks like a cardboard after the effect of motion distortion has been compensated. However, for making IMUs do this, we have to know the extrinsic calibration or the spatial separation between both these sensors. And not only for this, we need to know the spatial separation between LiDAR and an IMU in any kind of LiDAR IMU SLAM algorithm or LiDAR IMU odometry algorithm. So the goal of this work is to estimate this extrinsic calibration or the spatial separation between a 3D LiDAR and an IMU. Since IMUs sense only motion, we have to do, which is popularly called in the calibration literature as motion-based calibration. Now, motion-based calibration involves the individual sensor motion for doing extrinsic calibration. A schematic of that is shown in figure 3, where you can see IMU motion, which is denoted as TIK-1 IK, and LiDAR motion, which is denoted as TLK-1 LK. And the individual sensor motions are related to each other via the extrinsic calibration parameter TIL. And this relation is shown in equation 1, which is also called the motion-based calibration constraint. So now that we have established this constraint, we follow a two-step approach for doing extrinsic calibration. And for step 1, what we do is we try to initialize the rotation between both the sensors using just the rotation component of this constraint, of the motion-based constraint that you see in equation 1. And then once we have that constraint set up, we solve a nonlinear least square optimization problem. So step 1 gives us an initialization. So once we have the initialization of the rotation between both the sensors, we use a Kalman filter-based approach to estimate the translation between them. And the Kalman filter-based approach uses the entire motion-based calibration constraint for doing measurement update under an EKF framework. This slide shows the step 1 of the process, where you can see that the LiDAR measurements are going into a block called NDT scan matching. NDT stands for normal distance transform scan matching. Long story short, it basically is used to determine the pose between two LiDAR scans. We get the full 60 OF pose, but here we just extract the rotation part of it, and that is denoted as RLK-1 LK. And for the same duration, we also do gyro integration from the IMU measurements, and that gives us the IMU rotation between these two instants. So that is RIK-1 and IK. So once we have the IMU rotation and the LiDAR rotation, what we do is we form that nonlinear least square problem that I was talking about previously. And that is shown both in figure 4 and figure 2, where you can see that the optimization problem is stated. And we solve it using standard libraries like one can use Cirrus or GTSAM, any standard or N-locked to solve this particular problem, and that will give us the initial rotation between both the sensors. I call it initial because in this particular step, we do not account for the biases that are present in IMU. And that's why one can say that this rotation estimate is not actually the final estimate, and it needs some refinement where we estimate the biases as well. And for that, we use the Kalman filter-based approach. So we use this initialization to to initialize the Kalman filter. We feed it as a parameter into our Kalman filter, as you can see here, where you can see our IL init or our IL initialization is going into that block. I'll just briefly present the block diagram here. But before that, I want to state that for the Kalman filter-based approach, our state variable comprises of the IMU pose, velocity, IMU biases. This is the evolving component of the state. And in addition to that, we have a static component, which is the extrinsic calibration between both the sensors. That is denoted as TIL. You can see that in the first and the second line of this slide. So we have an evolving component and a static component. Our goal is to estimate that evolving, our goal is to actually know the static component, but one has to also estimate these evolving components in order to get this static component. So they come as a part of the solution. So once we have IMU measurements, what we do is that we predict it forward in time. So that's called the IMU propagation. We use discrete time IMU propagation model to predict it forward. And at the same time, we use that prediction model to de-skew the LiDAR scan, because since the process is basically based on motion-based calibration, we have to move the sensor suite while collecting the data set. And when we are moving it, the LiDAR scans undergo severe motion distortion, and we have to de-skew that during the calibration process using the best estimate of the extrinsic calibration and the IMU measurements that we have at that point. So once we de-skew the scan, we have like corrected motion compensated scan available. And once we have the motion compensated scan available, we perform NDT scan matching on that, which gives us the LiDAR motion. And that LiDAR motion is used for measurement update. So by the time one reaches the EKF update block, they already have this IMU state propagation or the state prediction. And we also have these measurements. And using the measurement and the prediction and also a measurement model, we perform EKF update. I'll briefly touch upon the EKF measurement model here without spending much time on it. So one can rearrange the motion-based calibration constraint that we saw in equation 1, and they can come to equation 3. Now, equation 3 is analogous to the measurement equation that we use in a standard Kalman filter framework, which is Z equals H of X. And Z here is the measurement, which is the LiDAR scan matching result, denoted as TLK minus 1 LK. And H of X is the measurement model, which is basically a function of the state variables. And you can see that the right-hand side of equation 3 is basically comprised of those state variables, which is TIL, which is the extrinsic calibration parameter, and TGIK minus 1 and TGIK. These are like the positions or the pose of the IMU at K minus 1 and K. Once we have this measurement model and the predicted state variables and the measurement itself, we can form the residual that one can see in equation 4. And there you can see a log term, which is basically used to map elements lying on the spatial Euclidean group to R6, a 6 vector. And I don't want to go into detail here in the interest of time, but that's what it is. Like we have the residual there. And once we have the residual, we can perform the EKF state update. But in addition to that, we also have to perform EK covariance update. And to do that, we have to calculate the Jacobians of the measurement model H of X, which is a fairly involved process. And again, I skip that here in the interest of space and time. Now, in this particular slide, I present to you the sensors that we have used. You can see that on the right, there is a Ouster 128 channel LiDAR, which gives out LiDAR scans at 10 Hertz. It can be configured to 20 Hertz as well, but we use, in our experiments, we use 10 Hertz scans. And the one on the left is that you see in red is a VectorNav 400 Hertz IMU. Now we have also demarcated two different locations here, location 1 and 2, which are about 5 centimeters apart as far as our ruler measurements are concerned. So there is some error with that measurement also. And we use this particular information for validating our calibration algorithm. And how we do that, I'm going to talk about in a later slide. Now coming finally to the experiments that we did. So in this particular graph, I show the convergence property of the extended Kalman filter we have used. And this is for the translation variable. And since we do not know the translation between both the sensors, we just start from 0, 0, 0. And then you can see in this curve how they have nicely converged to fixed values with tight 1 sigma bounds. So that is what we expected. That is how we expect the Kalman filter to work as well. So one can say that it is working, as far as the convergence properties are concerned, it's working well. Similarly, the same result is seen for the case of rotation between both the sensors. However, since we had initialized rotation and our initialization method works pretty well, we do not see much change in the refinement process. And that's why you can see that it's more or less fixed all through the along the time axis. And also we have plotted the 1 sigma bound for reference. In this particular slide, I show the importance of de-skewing the LiDAR scans during the calibration process. Now, inside the calibration process, we have an NDT scan matching step. If you do not de-skew the scans before doing NDT scan matching using whatever best estimate of the calibration parameters and the state variables we have, then the result we are going to get finally is going to be bad. And the first thing that you see here, if you do just raw scan matching without de-skewing it, you'll see a lot of misalignments here in the corner. And also the corners are not sharp. But once you de-skew them using the best available estimates, you can see that the corners are sharp, right? It's motion compensated. Consequently, the result of LiDAR motion estimation will be better with de-skewed scan matching, and that will result in better calibration estimates. And that you can see in this particular slide, where the orange plots show the result of calibration when we do not de-skew the scan. And the blue shows the result when we de-skew the scan. So the orange is not converging well, or whenever it is, it's like jittery, it's noisy, it's not good. But the blue plot looks fairly decent. So one can say that raw scan matching results in inferior estimation of LiDAR motion, leading to inferior calibration estimates. In this particular slide, I try to show the effect of how our algorithm is robust to different type of LiDARs. Although we just use one LiDAR here, but we can still downsample the LiDAR and the number of rings in the LiDAR just to simulate the effect of a different LiDAR, because in the market there are different kind of LiDARs available with different channel numbers. So we do our experiments for 128 channels, which is the default setting. And then we do it again for 64 channels, 32 channels, and 16 channels. At both the locations that we had collected data. And within the table, you can see that the results are comparable, like along each axis. They are very much close to each other, irrespective of the number of rings. And the same result is also seen in table 2 for location 2. So the idea, the point that I'm trying to make here is that our calibration algorithm converges to comparable estimates of calibration parameters at both the locations, irrespective of the number of rings or channels. Now, in this particular slide, we perform relative verification of our calibration algorithm. Since we do not have access to ground truth, and because it's virtually impossible to know the exact center of both the cameras, both the sensors when they are placed together, because we are not the manufacturer of the setup. We procure cameras from third party. So we do not know the exact center of both the sensors. That is why we perform relative verification. And we also do not have the auxiliary sensor at our disposal, where one can reproject points on a LiDAR, on a camera, and see if the reprojection is good. Even though reprojection is not probably the best way to validate algorithms, because it results in loss of dimensionality because there is some loss in dimensionality. Because calibration is basically a metric problem where we are trying to estimate something in 6 degrees of freedom. So the error matrix should also be in 6 degrees of freedom. But when you are trying to verify it using reprojection errors, then we are actually going from 3D to 2D. So we are losing a dimension. And I don't think it is the best way to verify. However, coming back to the topic, in relative verification, what we do is we collect data set from 2 different locations, and we know the difference between those 2 locations. And we run our algorithm for both data collected from both these locations. And we take the difference of the results that we get. And that difference should be close to the measured position between both the locations, which was 5 centimeters in our case. And you can see along y-axis here, irrespective of the number of rings, we are getting results which are close to 5 centimeters, if not 5 centimeters. And the percentage errors are also written in the table below. So one can say here that with certain error bounds, our calibration algorithm is actually converging to good estimates. So finally, summarizing our contribution, we presented a simple EK-based 3D LiDAR IMU calibration algorithm that does not depend on any target or spatial environmental augmentation like presence of planes or lines. We do not use any auxiliary sensors like cameras or GNSS for the calibration or the verification process. And we also presented the usability of our algorithm for different channel modes, for different LiDAR densities. And finally, we also open source our code for the robotics community. As far as future work is concerned, we really want to incorporate temporal calibration between both the sensors, thus bringing together extrinsic calibration and temporal calibration and combining it as a generalized cross calibration solution. Thank you so much for your time.